fact which we have used in the proof of Kunneth theorem, yes? Something like this. If we have a chain complex which in each level has the following form: boundaries, previous boundaries, yes, and homologies and differential acts like this. Zero, identity, 0. It's differential, and if we have one such complex and another such complex, then the homology of their tensor product, it's tensor product of homologies. No, it's just Hi and Hj. And this. Okay? Did you prove this?
Yes.
Okay, you're welcome. In fact, we have used only for projective chain complex, and this is maybe a little bit more obvious, but no, it's true for general complexes, so you're welcome. General splitting complex of such form.
So before I proceed, I want to correct myself. I had a mistake on the last time. I want to correct myself. So the mistake was like this. So and because of this mistake, I said yes. I said a lot of stupid stuff afterwards. So in extensions, so yes, I have it here. So in extensions, we had an isomorphism map like this. GCD of Mn goes to Zm times n Zm. So, and I wrote that these maps goes like this. And by D, where D is this is D, D times K. So this is not correct.
Yes, it's what I was caring about. It was not obvious for me.
So the correct formula is like this. When I wrote, when I proved this isomorphism. So the funny thing that when you asked me why is it true, I even wrote the correct stuff here when I thought about it, but I I don't know, I just erased it. So so we have when I proved this formula, I used this map phi from Zm to Zd, which is maps k to k. This is phi, yes. And it turns out that from the homomorphism theorem, this is surjection, and from the homomorphism theorem, we had that D is isomorphic to so Zm times the kernel, and the kernel will be here n times so yes, n times Zm. And so just to see that the correct formula for this map is that k goes to class k, and to see this you need to just look at how the isomorphism in the homomorphism theorem works, but this works just like this. You need to take k in another direction, I guess. In another direction. Yes. Yeah. I just sent k to phi of k to the class phi of k, but this is k. So this is everything. This is now. So the correct formula is like this.
Class on the left is modulo d, and class on the right is modulo n Zm.
Yes.
Something like this.
Yes. So this is this is the correction, and hence, as I said, I have so in the internet says one thing, and I have another. solution. So everything matches now, and we have extensions from 0 to d minus 1.
No, yes.
Everything is
exactly d extension.
yes. So this is a correction.
Okay, it's very well. So, good for you to understand the correction.
Yes.
Okay, what about the complexes?
Yes. So let's see if I did it correct.
Is it hard?
What do you mean?
This proof?
No.
Okay.
How have I done it? So, so I need a lemma. A lemma is like this. A lemma is like this. So if I have one chain complex which is homotopy equivalent to another chain complex, then total chain complexes are D are homotopy equivalent to each other. E under D. Just like this.
Well, I think it's more or less obvious.
Yes, this is obvious. The proof is just by direct calculation. So
yes,
yes.
you can construct homotopy on tensor product by identity homotopy on D and homotopy on C between A.
Yes, yes, yes.
Like, okay, it's obvious. Okay.
Just tensor product. Okay, so this is obvious.
Yeah.
And so maybe you consider this cheating, but so now proof of this theorem.
No, you can use anything what you want. Just don't use Kunneth formula.
No, not Kunneth formula. I just use the fact that I proved several lectures ago that this is homotopy equivalent to H. So I proved it actually for vector spaces, but from vector spaces I used from this formula I used the only fact that
like
it decomposes.
Yes.
I proved this several lectures ago.
Yes. No, for vector spaces you're right, but you use something like this decomposition, yes? And,
yes, but now
it's true for such complexes.
Yes, but now I don't use. So now I just have this decomposition, and
yes. So you have such a homotopy. It's okay.
Yes, this is obvious, and for D it is also obvious. I mean, not obvious, but I proved it.
It was proved. Yes. It was checked for chain complexes, essentially for chain complexes with such decomposition.
0. Yes.
Okay.
So and now the proof is in one line. So total complex of C tensor D.
Okay, yes.
Yes, is homotopy equivalent.
The total of homology is 0 complex, and this is chain complex with 0 differential.
Yes. Yes. So this is total complex, and here, yes, we have 0 differential. So this is 0 differential, and this is obviously
this is what I
direct sum plus B
exactly.
A.
No, it's okay. Tensor product.
Yes, yeah, of course.
Okay. Yes, you're right. Okay, very well. Okay. And we have used this in the Kunneth formula, okay? Yes. Okay. Thank you. Today I want to, on seminar I want to talk something about on topological and geometric applications of spectral sequences. Some examples of such things. The first example, 1 second. Yes. Kunneth formula. Yes. The first example is check the Rham spectral sequence. Now let we have, first of all, let we have simplicial complex. Do you know what is this? Simplicial complex. No, it's abstract simplicial complex. It's just number of some. It's some set of vertices and some abstract subsets of some subsets of K such that with the property that if some distinguished subsets of K, which we call simplices of our simplicial complex, such that if is simplex, then any subsimplex of simplex is also simplex. Okay, it's a definition of abstract simplicial complex. Okay. Then we have definition. We can define simplicial homology. Simplicial homology. We can define simplicial cochains. Something like n of K with some coefficients in some abelian group. I want to define something like it's just maps from K n times to A. It just maps. Oh no, maybe yes, such maps. It's abelian groups because it has abelian group structure from A. Yes, again, it's formally it's okay. Maybe yes. Let me formalize definition again. If K is set of vertices, then some family. We say that this set of vertices has structure of simplicial complex if we distinguish some subsets, okay, with this property, simplex, then simplex. Then we say that its structure of simplicial complex on K. No, and maybe we will assume that all vertices are simplexes. Okay. Then we can consider such cochains. It's just functions with the value in with values in some abelian group on ordered sets of vertices. Okay. Oh, maybe yes. Maybe. No. Okay. But with we will consider skew symmetric functions such that it goes to f of K and with this property that if I permute this vertices, then value will differ by sign of permutation. Yes, we have some simplicial complex, abstract maybe, maybe geometric, it's finite complex. And this is cochains, simplicial cochains. Maybe usually you consider just all cochains. It's without this assumption, it's just usual cochains. Because usually you consider. No, sorry, it's not true. Okay, stop. Sorry. Sorry. It's nonsense. Let me define Kn. It's subset of n simplices. Okay. It's ordered. It's ordered tuples and tuples of vertices of simplexes of my simplicial complex. Okay, it's not every tuple is some simplex. It's exactly simplex. Okay. Okay.
So Kn is simplex.
It's a subset of all vertices of simplices. K1, Kn lies in Kn if and only if. This is simplex in K. Okay?
the set of vertices or K is simplex itself?
Okay, I did not do the same thing. Okay, let something like this. This is my simplicial complex. Okay, then this is simplex of the simplicial complex. It's just the set of some distinguished subsets of K, which we call simplexes with this property. Yes. And this is set of simplexes. And okay, now just usual simplicial cochains, it just maps from n simplexes to abelian groups. It's abelian group, and this is usual. We assume also this skew-symmetric property. No, it's a well-known fact that this property ну, как-то does not influence, I don't know, как не влияет. Ну, короче, оно не влияет на гомологии. This property does как-то with this assumption, cohomology of this cochain complex, simplicial cochain complex, is the same as the usual simplicial cohomology of simplicial complex. Okay, yeah, it's true. So okay, and we have usual simplicial differential. Okay,
cohomology of this complex, cohomology of this complex will coincide with the usual.
Yes. It's more or less no, it's a fact about simplicial cohomology. When you consider co-simplicial cochains, you can assume that these cochains are skew-symmetric, yes. Because they automatically skew-symmetric on homologies, in fact. It's exercise, if you want. So you can assume that they are skew-symmetric originally. They does not depend on, no, homologies does not depend on this assumption. Simplicial differential is the following, yes. It's an Ka to Cn plus 1 Ka. If I have some function, it's some function on n plus 1, and this is sum, yes. Okay. Without yes. No, this is usual simplicial cochain differential. Yes. Oh my God, sorry. Yes. N-dimensional simplices has n plus 1 vertices. So it's n plus 1 here. It's from 0. Yes, okay. It's from 0. Yes. Yes, and here I have, yes, it's plus, right. Okay. And cohomology of this chain complex is just cochain complex. It's just simplicial cohomology of your simplicial complex. Okay, usual one. Okay.
But the complex is different.
Groups a little bit less. Yes.
No, or is it isomorphic? Because it's not really obvious for me. But
maybe it's an exercise. Yes, you can compute usual simplicial cohomology using skew-symmetric cochains. Yes. It's a dual proposition about that. If you want to compute simplicial homologies, you can use usual chains, but modular permutations. You can consider if you differ vertices of some simplex, it's the same as the sign of some permutation, and this is what. And this is simply what modulo this. You can use this quotient complex to compute the original chain homologies, simplicial homologies. It's the dual things. Yes, it's right. No, it's exercise. Yes. Okay. So the homology of this chain complex, it's homology of simplicial chain complex with coefficients in A. Okay. Okay. Now, if we have X is topological space, and we have some
K hat maybe, not K.
No, of course, yes. Yes, no, of course it depends on simplicial complex structure. If we have X is topological space, then let me have some open cover of this space. Yes, it's U. It's open cover. It's some set of U alpha, such that X is union of U alpha, and it's open subsets. Then we have on this set we have structure of simplicial complex is nerve complex. Nerve complex of this cover. Nerve complex. How завитушка. No, it's simplicial complex on set of my covering subsets, and tuple of subsets is simplex if and only if their intersection is not empty. It's namely simplicial complex because if intersection is empty, all less intersections also not empty. So it's simplicial complex. Okay, it's called nerve complex. It it's remember the combinatorics of intersections of your cover. Okay. It's definition. It's usual thing, in fact.
I have the problem, just formal problem. When I have simplicial complex is some subset of 2 in power of. You see, but here you consider ordered.
No, so in fact, it's not ordered because this property does not depend on order.
Yes. Okay.
Yes. Yes, and this is yes. You're right. And this is, in fact, this is essentially the the caution, как сказать, причина. This is cause. I don't know. It's why we consider skew symmetric here, because here it's ordered tuple. No, because to define function we have ordered tuple of vertices, and here unordered tuple. Yes, and so this is forgetting ordering. It's skew symmetric assumption. It's because of this. You're right. Yes. Okay. This is simplicial complex, nerve complex. It's a remember combinatorics of intersection of cover, and you can consider the homology of this simplicial complex. Cech-de Rham theorem says that for a smooth manifold, for small enough covers, they coincide with the Rham homology. Why? We now prove this. In general, if you consider direct limit for more less and less covers, it's called the Cech homology of topological space. It's limits over all covers of such simplicial homologies. It's called Cech homology. So in fact, Cech-de Rham theorem says that for manifolds, the Rham homology coincides with Cech homology with real coefficients, where it's real numbers here. Okay. Let me say something about this. Now I want to define B complex, which.
By the way,
I
need this part. So Kn, when you wrote f from Kn to A.
Kn is a set of ordered tuples of vertices. Yes, you're right. Such that an ordered tuple is simplex.
Yes. But what do you mean by map? So what is A?
It's some abelian group.
It's some abelian group.
And if you have maps from set to abelian group, it's abelian group because you can add as values.
Yes, okay. So just all functions. I mean all functions.
With skew symmetric from simplexes and with skew symmetric assumption. Yes. Okay. Now I want to define. No. Yes, and also. Okay. Let M is smooth manifold. We also have the Rham the Rham chain complex, cochain complex. Yes, we have. Yes, we have the Rham differential. Yes, it's cochain complex, and its cohomology is the Rham cohomology. Yes, it's. I think it's familiar for you. Yes. The Rham cohomology. Now I want to define some B complex which generalize this thing and this thing for manifold. So you have manifold, and I have some open cover of this manifold. Open cover. I can define the following B complex. Homological type B complex of this cover. No, it's just it's abelian group. It's vector space of its maps from K P to Q differential forms on the corresponding. Okay, sorry. How would say? No, yes, it's set of functions from if I have ordered tuple such that of vertices of my nerve complex, such that it's simplex. So it corresponds to it's numbers of my subsets of my cover which with the non-empty intersection. Yes. Then element of my thing is it's sends such simplex to some differential form on this intersection. Again with skew-symmetric assumption. So for any P simplex, it sends this to some differential form on intersection with skew-symmetric assumption. And all of these things are vector space, and these are vector space.
This is map is from KP to
no, to direct sum of all ohmic, because it takes values in different for different simplexes. It takes values in different form on different subsets. Okay. No, for different simplexes, it takes value in omega on different intersection. Okay. So in fact, it's something like Kp to direct sum of omega q of all intersections over all Kp, and such that simplex takes values in the corresponding direct summand. Okay, something like this. No, formally saying.
I still don't understand. What is the direct formula? So this is map from where to where? What is the
Okay, formally saying it's something like this. It's from simplices to direct sum of Q differential forms over on intersections over all simplices such that element some simplex takes value in the corresponding direct summand only. Something like this. Okay.
What do you mean that simplex takes value?
No, it's some function, and their value on the simplex, in fact, it's not direct sum. It's just one summand corresponding to this simplex, intersection to this simplex. Okay.
Okay.
With skew-symmetric assumption. If I permute these vertices, I need to add some sign on this differential form. Okay.
Okay.
such functions. Mhm. I have cochain simplicial differentials here and the Rham differentials here in two directions. No, yes, it's C P Q C P plus 1 Q. No, it's if I have such function C and on some chain complex P plus 1, it's the same formula. It's C on K0 without Ki, K P plus 1. This form defined on its form from Q on this intersection without UKI. It's and I need a differential form on intersection of all these things. No, I can restrict it on intersection of all UKP plus 1. No, in fact, this differential form defined on the a little bit more set, okay? A little bit bigger set. Okay? No, by definition, they think this differential form is defined on intersection of all Ki without Ki. Yes. Here I need to define differential form on intersection of all Ki. So it's defined on the bigger set, and I restrict it on the smaller set, on the intersection of all the things. And do this for any summand, and I obtain the differential form, okay? Yes. No, and I have the Rham complex. No, it's just the Rham. No, just apply the Rham to the differential forms, okay? It's from PQ to PQ plus 1. Now you can check that this is in fact, they commute. D de Rham and delta de Rham, they commute. Now if you want, it's exercise. It's a direct check. So we obtain, not exactly chain B complex. No, it's B complex modular some changing of some signs. No, because if or you need to consider total chain complex with this differential. Yes, it's to be this homomorphism square 0 because of this equality, you need minus here. If you consider plus here, you need something here, something minus here, and this is you can redefine, for example, delta by something like this. By some signs in odd p dimensions, for example. No, I think it's not important. I just want to say that it's not important, in fact. Okay, we can consider total complex with minus, and this is chain complex also. No, I just want to say that this sign is not important for us considering spectral sequence and so on. Okay. Okay, I have B complex. So I want to consider its spectral sequence. Two spectral sequences. Oh, yes, maybe yes. I want to say that in fact this B complex, this total complex, has it has almost exact rows and columns. Almost all these columns and rows are exact for small enough covers. Let me state it a little bit more strictly, a little bit more accurately. Yes, I have such B complex. It's called Cech-de Rham B complex of this cover.
So can I clarify the Rham acts like post-composition?
No, the Rham is just applying the Rham for the for values of the yes post-composition. Let me assume that U is cover is numerable. Numerable. Do you know what this means? No, it's numerable. It means that this cover has partition of unity, partition of unit. There exists number of smooth maps, smooth functions, such that they are locally finite, and their sum exactly unit and subpart of any rho alpha in U alpha.
So do we need to say that U is like for every point there exists a finite?
It's not important. No. I just want to that for any point there exists neighborhood such that in this neighborhood only finitely number of this function are not zero to define this sum. Maybe original cover is not. It's not important. For me, importance is locally finite of this set of functions to define this sum.
Yes, okay.
But each support is where it's not zero closure.
And it always exists because manifold is paracompact.
Yes. For any smooth manifold, of course, yes, such thing exists. Okay, and if we consider, yes, we have for smooth manifolds, it always exists. And then, if I choose some partition of unity, then I can define the following operator, the following map D from CPQ to CP minus 1Q. It's just dc of some function on kp minus 1 is sum overall k, it's element of my partition of, and also it's vertex of my complex, of my nerve complex. And I consider rho k, it's number of my indexes of my covering, and this is k, k0, kp. This is some differential forms defined on the intersection, but yes. But this function is zero outside this cover, this subset. So in fact, all the sums defined on all this intersection, and I can consider the sum. No, it's exercise correctness if you want, and exercise is.
Wait. So rho k is a map from M. So you need to put
What map?
Rho.
Rho, yes.
Is a map from M.
Yes.
So it takes values in M.
In R. In R. It's
yes, values in M, but it's domain is M.
Yes.
So you need to substitute a point in there of M. You need to substitute rho of x of.
It's differential form.
No.
I multiply differential form by function, and this is also differential form. They all things in some x and m. It's also differential form. It also has in fact in some point. Yes, it's differential form. Its differential form depends on vertices. In fact, it's itself in some point. In fact, yes. This is function, and this is differential form, and this is again the form.
But wait. So C is defined only on.
These things defined on intersections. So but because this function is zero outside UK, in fact, these things define on this bigger intersection, in fact. No, it's zero outside the K. No, if you want, please check correctness. It's exercise. It's more or less usual extension by zero.
No, I understand what you want to say, but what is written is incorrect. Because you are summing the K runs over whole U, overall cover U.
Each summand is correctly defined as this thing. Check this. It's exercise. And another exercise, exercise is correctness is exercise. And another exercise is that it's more or less chain homotopy with respect to delta differential with identity and zero. That d delta plus delta d is identity. no, where it defines. So for p more than 0. No, to define this set. Mm-hmm. So in fact, we obtain that if cover is numerable, then the homology of this B complex with respect to delta is 0 for p more than 0. Is what I want to say with this construction. Okay, what the zero homology? What the zero homology? What is it? Okay, let me clean the board. Okay, you remember this formula, and no, next time please say me why it's not incorrect. Okay, or why it's correct. Let's compute a zero homology. What the zero homology of this B complex? Of this complex, yes. No, it's just what the it's kernel of C0 K 2. Sorry. No, yes. 1 second. No. Yes. The delta. And what is it? No, maybe I didn't say what the C0Q. No, C0Q is differential forms. Its functions. No, it's differential forms which are defined on intersection of zero number. Intersection of zero number is whole M. So this is by definition it's omega QM. Oh no, sorry. No. Oh, no, it's okay. Sorry. This is by definition it's functions from zero simplices. Zero simplices is just open covers of my sets. It's functions from open cover to differential form on this subset. And differential here say that DC on two elements of my cover is just it's just difference between their values. No, restrict to intersection. Okay? And so if it's 0, then in fact these parts glue together to the global differential form, if and only if. So kernel in fact is global differential forms. Because by definition it's some differential forms defined on the open cover such that they coincide on intersections. So it's exactly differential forms itself. So this is zero homology. Okay. Very good. Now we consider the homology of this B complex with respect to the Rham differential. Remember these things. Okay. What they think? If I fix P, then this B complex, in fact, as I said before, oh yes, I said before this is direct sum. It's not direct sum. It's even direct product because it may be infinite, and so this is direct product over all simplexes, K simplexes, P simplexes, yes, P simplexes of these things. No, it's as I said before. And this is, in fact, direct sum of chain complexes with respect to the Rham, because the Rham differential, it preserves this decomposition, because it's preserved. If I apply the Rham differential to differential form on intersection, I obtain also differential form on the same intersection. So this decomposition preserved by the Rham thing, and so. In fact, with respect to the Rham thing, I obtain just direct product of these de Rham chain complexes. Okay, So the homology.
Wait, can you repeat why is it true that it decomposes?
No, because it's
And why is it Q there? Or you wrote omega Q?
what?
I mean, you wrote omega Q on the right and never wrote it on the left.
No, yes, no, Q is this Q, yes. No, it's because by definition, my function, no, what's the element of product? Product is by definition, formal definition, it's number of function from indexes to values. And this is by definition my functions. Okay? Maybe, okay. Yes, maybe it's not KP here. It's because I have skew symmetric assumption exactly to say this is not KP. It's just over unordered simplexes, unordered sets. Yes. It's simplexes, unordered simplexes, yes. It's because, in fact, my direct product, I can consider direct product over ordered by skew symmetric assumption. In fact, no, it's in bijection with direct product over unordered simplexes. Okay. And this is direct product of chain complex, and easy observation that direct product and direct sum, they preserve homology, they're exact functors. No, homology of direct product is direct product of homologies, okay? So cohomology, Q cohomology of this thing is just direct product of my P simplices of my K. It's the Rham cohomology of intersections. Okay, now okay, it's very well. Now the cover of smooth manifold called Leray cover, if all non-empty intersections gamomorphic to open balls. Leray cover if all non-empty intersections gamomorphic to open balls. Such covers always exist, and moreover, you can embed to any cover such cover, smaller cover. It's something like geodetic balls or something like this. You can prove this, for example, by considering some Riemann metric, but it's true for any smooth manifold. And so, if we consider such cover, no, it's fact from differential geometry that it's true. If you consider such cover, then all this homology are zero again if Q more than 0. So for such covers, this is 0 for Q more than 0, and what's 0 homology? I obtain something like P R, yes. No, it's exactly, no, yes, it's over simplexes. It's exactly this thing. It's just functions with constant terms, with constant values. In values, it's my the Rham cochains on nerve with values in R. And delta differential is exactly delta differential on this thing. No, because my zero cohomology is just R, and so this is constant functions defined on simplices. Zero cohomology. Q cohomology are 0. And zero cohomology of ball is just R.
Yes.
And I obtain R. And this is the same as functions on simplices with values in R. It's my cochain. It's my cochain. It's my cochains. So what we obtain? We obtain, if we consider numerable and Leray cover of smooth manifold, then we obtain that we have be complex, first quadrant, such that all rows, okay. Consider the first spectral sequence. PQ. It's homological. So yes, it's PQ. D delta, for example. Then, with respect to D, I obtain it's just one row, one row. No, one column if P is 0. It's not 0 if only one row if Q is 0. This homology is only when Q is 0. It's one row, and it's in differential delta. And this is my, in fact, cochain complex of NU with R values. With differential delta, usual simplicial complex. So the homology is just the Rham homology and simplicial homology of my nerve. On the other side, for the other spectral sequence, if I compute in another direction, in another order, at first I obtain again 0 except one column where it's the Rham forms with the Rham differentials. So when I compute its homology, I obtain P the Rham homology. P the Rham. And now, and so we obtain that in each spectral sequence I have only one row or only one column. So in fact, this nth number coincides with the nth homology of total complex, and so they are isomorphic. So in fact, from these two spectral sequences, I obtain that in fact this cohomology, for Leray cover, we know that all are numerable. I obtain that n cohomology de Rham isomorphic to n cohomology of this total complex of this Cech-de Rham complex, and this is isomorphic to from another spectral sequence to simplicial cohomology of nerve of this complex. For smooth manifolds, as I said before, you can substitute any cover to Leray cover. So, in fact, Leray covers are the cofinal set in the set of all covers. And in fact, if you consider direct limit of these cohomologies over all covers, this is by definition Cech cohomology with R coefficients. They also coincide with the Rham cohomology because you can compute them by using only Leray covers, and for all Leray covers they coincide with the Rham cohomology. So such pretty application. Yes, that for smooth manifolds we obtain that the Rham cohomology coincides with the so-called Cech. Or you can compute them by consider some good cover and consider simplicial cochains, yes, of the nerve, something like this. Okay. 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 Also, for example, if you consider complex manifold, then, as you know, maybe, that on complex manifold, your forms, your differential forms, if M complex, then differential forms is a direct sum of PQ forms. Yes, you have P galomorphic and Q anti-galomorphic differentials. Yes. Okay, you know this.
I only heard about this format.
So it's because if you have M is n-dimensional complex manifold, then if you have complex coordinates, it's complex coordinates. But if you consider such coordinates and conjugate coordinates, this is 2n real coordinates on 2n dimensional real manifold. It's real coordinates on M2n as a real manifold. And you can write down any real differential form. It's real differential forms in terms of these coordinates, and so you obtain some p forms. Any form has you have coefficients some z, and others are q, other conjugate. This is p plus q. And in fact, your the Rham differential is the sum of differential on galomorphic forms and differential on anti-galomorphic forms. In fact, it's sum of these two differential, and they anti-commute. So in fact, you have B complex. On any complex manifold, you have B complex. And if you consider spectral sequence of this B complex, if minus, yes, minus. And so you can consider B complex. No, you obtain B complex. And if you consider differential of this B complex with respect to d bar, you obtain so-called Dalbog homology. No, in fact, you obtain spectral sequence start with Dalbog homology. It's so-called, it's PQ. It's of M. It's just Q, P cohomology of this. Oh, 1 second. Oh, maybe I'm not sure again in indexes, but it's something like this. It's omega p d bar. Yes, it's the first page of spectral sequence. It converges to the Rham cohomologies. This is so-called Dalbog homologies, and no, it's isomorphic in fact to the homologies of M with respect to sheaf of differential in values in differential forms, but it's not important now. But no, this is so-called Hodge-de Rham of Fröhlicher spectral sequence. And for example, if M is scalar manifold, do you know what's scalar manifold? Scalar manifold is when you have your complex structure and you have also, for example, you have a metric such that Hermitian metric such that it's real. You have Hermitian metric such that it's you have complex structure. You have Hermitian metric and such that its imaginary part it's some skew-symmetric form, and this skew-symmetric form is symplectic. It's non-degenerate, something like this. It's differential of Kähler form. It's complex manifold such that there exists such a Hermitian form which imaginary part is symplectic structure. Okay, and in such situation, you have a lot of theory of Kähler manifolds. It's good manifolds. For example, all projective submanifold of projective space is Kähler, and all submanifold of Kähler is Kähler. So all projective manifolds Kähler, and if your manifold is Kähler, then this spectral sequence degenerate. They have all differentials are 0. So in fact, you obtain that all differentials are 0, and so your E infinity is E1. Sorry, it's cohomological, so yes, something like this. And so on nth diagonal, you obtain these things. And so you obtain so-called Hodge decomposition, that nth the Rham is not only for differential forms, it's true also for cohomologies. It's the Dalbog homology, it's the Rham homology. No, this is true only for, not for all complex manifolds, of course. It's true when this spectral sequence degenerate, and this spectral degenerate, for example, for Kähler manifolds. It's Hodge decomposition. No, even for some other complex manifolds, this spectral sequence is very useful because this Dalbog homology much more, maybe in some sense, more tractable from complex or formal algebraic point of view than the Rham homology maybe. And you obtain the spectral sequence because, as I said, it's some you can interpret them in terms of some shifts, shift homology, and so on. Okay. In fact, this is what I wanted to describe fast, and now I want to, it's something like geometry, and now I wanted to discuss some topology. Something like Serre spectral sequence, for example. No, maybe we will consider it next time also. And today in lecture, maybe we will prove some theorems about spectral sequences. Okay. It was some application in geometry, and now some applications in topology. Also easy, some first applications. Serre spectral sequence. Let me have vibration. Do you know what vibration is? Yes. No, it's a map with the property of the lifting of homotopes. Yes.
So this is Serre vibration.
Serre vibration, yes. No, it's because Serre considered such vibration and such spectral sequence for which it works, and it's so called Serre vibration after him. No, example criteria is fiber bundles. Of course, fiber bundles are Serre vibrations. For example, fiber bundles, okay. If we have such situation, then in fact we have two spectral sequences, homological and cohomological. We have homological spectral sequence of this form, base with QF converges to of E, and homological one. It's second page. Homological type spectral sequence, homological type spectral sequence. Here we need to say that no, in general, this is not constant coefficients. In general, you have so-called monodromy. If you have a loop in base, then any such loop acts on fiber. You have monodromy map. Monodromy map sends from fundamental group of base in some point to sets of homotopy maps from fiber to fiber over this point. It's monodromy. And in particular, you have action of this group, of fundamental group, on homologies, because any map of fiber induced a map in homologies and cohomologies. And by this action, you can define so-called local coefficient system with these homologies. And this is this local coefficient system. No, but in simple cases, when this monodromy action is trivial, this is just constant coefficients with homology, with homologies, okay? In general, this is local coefficient system. It's first one. Now, another one, of course, these spectral sequences are natural with respect to maps of vibrations, okay? Let's understand what I said. If I have map of two vibrations, then I obtain map of spectral sequences. Which
what do you mean by morphism of spectral sequences?
Morphism of spectral sequences, morphism of big-graded objects, such that it commutes with all differentials and so on.
Yes, okay. This is understandable. I thought that this implies something in convergence.
And on convergence, I obtain map on convergent sets, and they all what you wish, they all respect all structures, all spectral sequences, okay? I also have map of targets, yes. And if I have something like this. Maybe it's important because we will consider it maybe on this lecture. It's map. Of course, if you have such map, then you obtain map on homologies, but you need that the map on homologies also commute with the higher differentials and so on, okay? Then you obtain map on infinity page. And also you have map of targets, which respects filtration. And if it respects filtration, if you consider the induced map on quotients, it coincides with these things. Okay?
Wait.
Because convergence means that you have some filtrations here, and quotients are infinity, pq. It's on p plus q. And here you have these things. And this map on these things induced by this map must coincide with this infinity map, okay?
So F is a different map, so it doesn't come.
No, we have morphism spectral sequence. It's a sequence of maps on each page, on infinity page, and on target, yes, such that they all coincide. If you consider the next page as homology, then this map coincides with the map on homology induced by this map.
Okay, but if infinity is induced from, you can construct.
Yes, it's also coincides with induced, yes. And on this map, if you induced map on quotients, then it must coincide with this map, okay? No, all what you want. And this is our situation. The map of fibrations of course induces a map of spectral sequences. Is the second point, and the third point, important point, maybe which we did not discuss before, and maybe now it's time to discuss. It's multiplicative structure. It's important structure. It's very, in fact, it's very, maybe it's the most useful structure which can be raised in spectral sequence. It's very useful. If you understand multiplicative structure, you gain a lot of information from the spectral sequence. You can compute some differential for them. No, we will consider some simple examples. What's the multiplicative structure? No, spectral sequence is multiplicative. Now, what does it mean? No, you have spectral sequence of homological type, for example, homological type. Plus r, q minus r plus 1, dr. And it's what does it mean? It's multiplicative if all each page is begraded object, begraded module. And this begraded module is in fact begraded R algebra. Okay? That's what does it mean? Now this means that you have multiplications over some R a space begrading. Multiplications. No, associative with unit, maybe skew commutative with respect to the sum of gradings. No, I mean that AB is equal to minus 1 P plus P prime. P plus Q, P prime plus Q prime. BA, if A is from this and B from this. No, it's not a general assumption, but if we say it's commutative, we understand this in this sense. The skew graded commutative with respect to sum of gradients. Okay, we have such multiplication. Of course, differential satisfies Leibniz rule again with respect to sum of gradients. Oh, no, okay, it's not. P plus Q. This is for A. Okay, this is important. And on the target, if your spectral sequence converges to something, on the target you also need some multiplication, some structure of graded algebra. Our target is some graded object, it's some graded module. And this is also graded algebra. And we have filtration, decreasing filtration, because it's homological type, it's decreasing filtration. And this is graded algebra means that we have multiplication, okay, again of this form. And this filtration is multiplicative. This means that, again, if I multiply two elements of my filtration, I obtain this thing. Okay? This means that filtration also respects multiplication, or multiplication respects filtration. They respect each other. It's multiplicative filtration, okay? And from this thing, you can obtain multiplication on induced quotients. And this multiplication must coincide with multiplication on E-infinity page. Okay. In fact, it's very exercise. It's very important that in general you cannot reconstruct multiplication on algebra by multiplication on quotient. So exercise. Give two non-isomorphic algebras graded with filtrations, two different filtrations, such that on quotients multiplications coincide. So in fact, do you understand? I said it by words. Okay. Give me two examples of two graded algebras with multiplicative filtrations, such that the algebras are not isomorphic, but on quotients you obtain isomorphic multiplications. No, what I mean that, in fact, if you consider something like fp, fp h p plus q modulo f p plus 1h p plus q, it's sum over p q, for example. Yes. You also obtain multiplication of this thing.
So we cannot reconstruct multiplication.
Yes, in general, of course not. In general, of course not. In general, we cannot. We have some information, but in general, it does not enough to understand whole multiplication algebra. Of course not. Of course not. No, in fact, in this example, you can consider two algebras. No, it follows from you can consider algebra with non-zero multiplication, such that on quotients multiplication is zero, something like this. And then with zero multiplication on the same algebra, so it does not coincide. So in fact, in general, it's not. But for example, maybe we will prove it today. No, take answer at your home, okay? Today, maybe we will prove that if your E-infinity page is a free algebra, then your target is also free, and they isomorphic as algebras. Maybe we will prove this today. It's one of, if it's free algebra generated by some free skew commutative algebra. So it's generated by some elements. It's polynomial in even dimensional and skew polynomial in odd dimensional. If infinity is of such form, then target of the same form, and they are isomorphic as algebras. It's for free algebra. It's true. For not free, is not true in general. Okay. Some examples. And yes, of course, and the homological Serre spectral sequence is multiplicative. You have multiplication on this thing. Yes. Because you have multiplication on fiber and multiplication on homology, you obtain multiplication on this page, and you have multiplication on homology of E, and they all coincide. It's multiplicative spectral sequence. No, it's fact. It's from construction of Serre spectral sequence. It's multiplicative. It's important. Now I think today we cannot consider some examples. No, maybe we will start and then we finish next time. Some application of this Serre spectral sequence. Oh, for example, maybe what if we know? Maybe I wanted to give some ideas of the construction of the spectral sequence. Maybe next time. No, let's say something, some easy application. For example. Так, and yes, maybe important. for example, if here in fact I have some coefficients of my homological in some ring, for example. In general, it's not maybe integer. And if this ring is a field, if it's field, okay, then in fact this homology is just a tensor product. And this is big-graded algebra obtained as tensor product of two graded algebras. If you have two graded algebras, you obtain that tensor product is big-graded algebra, okay? If you have two graded algebras, you can obtain. Yes. No, no. be careful. Multiplication. Oh, it's important to obtain that multiplication if you have such thing and such thing. What the product? No, it's also casual sign here.
Yes, it's minus sign. That was.
Yes. This interchange. Yes. Yes. And then you obtain a big-graded algebra structure, and if they are skew commutative, then this will be skew commutative. Okay. It's because of this sign important. And this is our situation. Homology is skew commutative algebras. So okay. No, yes, and differential. It's if you obtain this differential graded algebra. So if they have differentials with respect which satisfy Leibniz rules, then differential defined by Leibniz rule. Yes. This will be differential on tensor product, and this differential satisfy Leibniz rule with respect to this multiplication. Okay, this is not Leibniz rule; it's Leibniz rule with respect to tensor product, but it satisfies Leibniz rule with respect to this dot product we defined before. Okay, on this big-graded algebra. Okay, so we obtain big-graded differential algebra in general. Now this is our case, I think. As homologies. Okay, for example, what first and maybe last today. Application. Let we have filtration with trivial monodromy without any not simple assumptions. And then I want to say the following. Let we have E, B, F. No, in fact. Fibrations with trivial monodromy called simple. Let's consider simple fibration. Then I say that I have three homologies or homologies. No, maybe homologies. For simplicity, it's not important. Then, and in fact, with some coefficients. Then, if coefficients is not very bad, if they are Noetherian. Then, if two of these modules are finitely generated, then third is also finitely generated. Maybe it's not very obvious from the first glance, but in fact, it follows from a spectral sequence. For example, if B and F finitely generated, then this thing is also finitely generated. Second page, finitely generated, okay? If homology of B and F finitely generated, then this thing is also finitely generated, okay? It's okay? No, it's okay. No, because this is also because this is already maybe from Noetherian, because I have I have a universal coefficient formula. Okay?
Yeah.
So this homology between tensor product and Tor. Yes, it's it's not true. Okay, in general I have Kunneth spectral sequence, but in Kunneth spectral sequence this is Tors, but Tors are finitely generated. No, okay, it's exercise for you. That is finitely generated for an Noetherian ring. No, for example, for Z or for field, it's almost obvious. And then I obtain that second page is finitely generated. Then all pages are finitely generated because pages are homologies, and the homology of finitely generated is finitely generated. This is where Noetherian is also important, because what is homology? It's kernel modular image. No, quotient of finitely generated is also finitely generated. It's always true. But kernel is submodule of finitely generated. It's not always finitely generated, but it's true for Noetherian rings. So homologies are finitely generated for Noetherian rings. So all pages are finitely generated. So infinity page finitely generated in each grading. No, I mean in each grading. Okay, yes, I mean for fixed grading, of course, finitely generated. Maybe the infinite one, infinite many, but each one is finitely generated. And so in each graded, because my spectral sequence is first quadrant, each diagonal is finite. So in each gradient, I have finite filtration of my target, of my homology of E. I have finite filtration, and in each step, it's finitely generated quotient. And again, it follows from if I have short axis sequence, if these two are finitely generated, then B is finitely generated. And so if I have quotients, all finitely generated, and it's finite, then in fact, by induction from this property, I obtain that this is finitely generated also. Something like this. No, because from filtration I have this short sequence. And another step. This we prove from this to this. No, for example, if I have these things to finitely generated, and why this is finitely generated? No, this will be from this to this one, it will be a symmetric argument. Why is this true? If it's not finitely generated in some degree, consider the minimal degree where it's not finitely generated.
Wait a second. So we used
no, we use something.
Okay, we used that in the first case. We used that H of F and H of B are finitely generated.
Da, and then I said that then this thing is finitely generated over Noetherian rings. Check this, and then we have spectral sequence. Yes. Now we also have spectral sequence, and let we know that homology of target finitely generated and homology of B finitely generated. While homology of F is finitely generated. Let it not finitely generated in some degree. Consider a minimal degree where it's not finitely generated. Okay. Minimal n where it's not finitely generated. It's P, Q, no, then maybe it's Q. Yes. It's something like here. Here, I think. No, yes, here it's exactly H, Q, F. Yes. The first column is homologies of F. Yes. Because it's zero homology of B with coefficient homology of F, it's just homology of F. Okay. Maybe I don't say it before, but zero column is homology of F, and zero row is homology of B. I assume that my base and F are path connected. Okay. I assume that it's our assumption. Okay.
You mean, once again, you mean they are connected?
Yes, B and F are path connected.
Okay.
And then this is just homology, okay? So we have some first degree where it's not finitely generated. But again, because all smaller homologies are finitely generated and all homology of B finitely generated, then all these things are finitely generated, okay, on this diagonal. Because it's smaller dimensions of homology of F and some dimension of homology of B, and I know that B all finitely generated. And again, from this thing, I claim that if this finitely generated and this finitely generated, then this is finitely generated, okay?
Can you repeat this?
No, I claim the following fact. If F PB finitely generated.
No, not this fact. The fact from.
No, I consider some. No, first number, minimal number where it's not finitely generated,
Yes.
and consider this diagonal. On this diagonal, I have these things where these numbers, q prime, no, except the first one, smaller than q. Okay?
First of all, this is page P2.
Yes, it's page. Yes, it's P2. I consider diagonal p prime plus q prime is equal to q. Q is my minimal number. This first one, where it's q0, it's not finitely generated, but all smaller are finitely generated because smaller homologies of f is finitely generated and all homologies of b are finitely generated. So I claim that this is finitely generated, okay?
Okay.
So on this diagonal, all finitely generated. And again, from this argument, I obtain that I have finite filtration of finitely generated thing, and all quotients finitely generated, and the last one is not finitely generated. It cannot be true if whole thing is finitely generated. It's cannot be true. No, because at the last time, I obtain its homological thing, so I have I obtain this differential. So at the last step, I have some finitely generated A, some E, and some homology of F. And this is homology of E. No, this is finitely generated, and so this is finitely generated with finitely generated kernel. No, in fact, I think it's even not important here because it's just quotient on finitely generated E. Then it's finitely generated, yes. Maybe it's not important then even. Yes, maybe here it's not important, but then it's maybe important for B, yes. If we consider B, I consider, no, it's for Noetherian it's also not important. I consider just minimal number, just maybe. No, it's not important, yes. Sorry, blah, blah, blah. Yes. Sorry, it's true. Yes, it's second page. Maybe I have some differentials, but it's for infinity page. I don't know, it's infinity page. Infinity 0q. But I claim that this is also not, this page must be finitely generated because it's quotient of finitely generated homology of EL, okay? Infinity page must be finitely generated, okay? But it's quotient. It's the first quotient of my target. It must be finitely generated. Now I want to say that this thing must be infinitely generated if this thing is finitely generated. Yes, it's the argument of diagonal. Yes, sorry. No, okay, it's true, but I have this first number and all these diagonals. But I think I need not this diagonal. Maybe I need the next diagonal, this diagonal also. And no, in fact, I need all diagonals. What I want to say that if this module is not finitely generated, it's second page. No, step to the next page. I need to consider homology. All these differentials are 0, okay? So it's some quotients. It's some quotients of images of the differentials from these ones. But all these modules are finitely generated because all lower homology of F finitely generated and all homologies of B finitely generated, okay? So in fact, except of this one, all these modules finitely generated, okay? No, it's the same thing. In all lower diagonals, okay?
No, I don't get it. I mean, this because we consider the smallest not finitely generated.
Yes, of course. I consider smallest not finitely generated, then all lower are finitely generated. So this is all finitely generated, okay? Because all B finitely generated, all lower F, okay?
Wait, the smallest
on F. No, on vertical coordinate, smallest.
So in Q.
Yes, it's Q. Maybe it's not finitely generated, but all lower finitely generated. Oh, hello. And if when I consider homologies, the next page, then I consider quotients by image. But image of finitely generated is finitely generated. And if I consider quotient of infinitely generated by finitely generated, I obtain again infinitely generated. I can't obtain finitely generated. So in the next step, this is also finitely generated, this is infinitely generated, and so on. And so in infinite page, I again obtain that this is infinitely generated. But it cannot be true because it must be quotient of finitely generated homology of E, okay? No, and for B, the symmetric argument. So we obtain the finitely generated nuclei. No, okay, maybe the next time we will consider another topological applications. And today on lecture, okay, let's break now. We prove some things about spectral sequences.